I have a question, kind of.
Yep.
It's more of like I was wondering if we could do a practice problem of the stuff we did last time for like Green's theorem.
You have one?
I've got one. I mean, yeah, I've got many, but I could just pick a random one, I guess.
Yeah, pick one that you thought hard about.
Um, okay, I'll just it's got one like find function f such that the gradient of f is equal to something else, right?
Okay, do
The
you have it?
Yeah, I do. I've got like f of xyz equals something.
Just share it on your share the screen. I haven't shared your screen yet, so you should be able to share your screen.
It says host disabled participant screen sharing.
Oh, yeah, we had this problem last time, and
Mhm.
Okay, I'm gonna do a quick Google here. Start your Zoom meeting, step the arrow. Okay. Okay, I can't uncheck these two things for some reason. Who can share? All participants. Okay. Okay, try now. Better? Yes? No?
You're muted, Chief.
It says I can share it if you want me to.
Yeah, okay, cool. Share it and let's at least everyone write the problem down, so and
It's
then we
just
can start.
This one's from WebAssign, so
Okay. Okay. So we've got this complicated curve here. You moved? Go down? What happened? Okay. Everyone copy that here. Anyone still copying? No? Okay, I'm gonna share now. Okay. Gonna go over here. Gonna make this full screen. Okay. So what's the first way we would draw a picture? What does C look like? So we've got y equals x. So this is 1, 2, 3, 4. Y equals x squared. This is y equals x squared. And this is x squared equal y, x equals y squared. x equals y squared. So our region is this thing, right? Okay. That sounds doable to parameterize. That just sounds doable to integrate over. But we want to use Green's theorem. So we're going to integrate. This curve sounds very horrible to parameterize over. And I've got this e to the square root x stuff in the exponent. Don't really want that. We're going to use Green's theorem. So what does Green's theorem say? This integral f dot dr, this is equal to the double integral over the region of what?
We do like your derivative of partial derivative of x to like the 10x plus cosine y squared.
Let's just go with, so what does it say? It says the partial derivative of q with respect to x, and the partial derivative of p with respect to y. So this is the derivative of this with respect to x, which is
Just be 10.
10 minus this derivative with respect to y,
5.
it's 5 dA. So this is just 5 times the area of this region, right? So how are you going to compute the area of this region? You could integrate, pretty straightforward. We got to find our bounds. This is a really bad picture, to be honest. Now that I'm looking at this, it's just like 1, 1 here. It's supposed to be 1, 1. That's where they intersect. Right, so find an equation for the limits of integration. And then it's just a simple integral. It has nothing to do with Green's theorem or anything else. Let me see if I can stop that glare. Okay. I mean, that should be that should be stuff from section 3 or 12, 15, when we first started doing multiple integrals. You set this up using Green's theorem, and this is essentially a trivial integral to evaluate. Okay. On that note, I want to go talk about something that I failed to mention about Green's theorem that is of interest. Maybe I can do this. I think I can do this. You can have like a side-by-side for previous ones. Yeah, we'll do that. So if I want to integrate, so what does Green's theorem say? It says this: p dx plus q dy is the integral okay. And here I didn't write this. I wrote this, f dot dr. So why are these the same? Okay, that's something that's we didn't quite talk about. But let's think about why they're the same. So if we take this integral, this is equal to integral over c of, let's say f is equal to p I plus qj. This is p evaluated at r of t I plus Q evaluated R of t j dotted with R prime of t dt. Right? And so this is the integral of C PR of t times the derivative of R prime in the x component dt plus QR of t derivative of the y component. I put two dt's there just to be clear. And what is this? This is this first part of the integral. PDX right here. And this is integral over C Q dy. There's an equal sign here. So when we're integrating a vector field, we're integrating the work done by a vector field, we can separate it into its components like this. Okay, and we talked about it a little bit in section 16.2, but to be a little more clear about it here in Green's theorem, because this is why it's of interest here. Okay, so we can add to this chain of equalities here, f dot dr. So this is just by definition. This bit is by Green's theorem. So we have a series of equalities that tells us how to deal with these kinds of integrals. Okay? So we're going to talk about two objects that are particularly interesting today, in the sense of they have lots and lots of applications in other places. And they show up in many other places, but the ideas will be interesting here, and they'll help us with some computations. So the first object we're going to talk about is curl. So if you picked up that book I told you to read at the beginning of the semester, Div Grad Curl, we talked about gradient already, and now we're going to talk about div, the divergence, and the curl. So we're going to cover all the three objects that I said were of interest. Okay, div grad curl. And later we'll talk about using these things to compute interesting quantities, right? Like how much is flowing through a given mesh, for example. How much stuff is passing through an object. That would be the flux, which we'll talk about later. Okay, and they'll have some nice tools for us to talk about conservative vector fields. We only really have techniques to determine if a vector field is conservative in 2 dimensions. We can guess in 3 dimensions, and hopefully it works out. We'll have some more sophisticated techniques to decide if it's conservative or not. And then we will see Green's theorem reformulated in terms of curl and divergence. Right? And that's going to be useful because as we move forward into Stokes' theorem and the divergence theorem, that's how they're going to formulate all their integrals. And Maxwell's equations are formulated in terms of the curl and the divergence and the gradient. Okay, so let's just define the curl, and we will see what it is. So the curl, if F equals P, Q, R, okay. So I have a vector field F. And I wanted to compute the curl. The curl is going to be another vector field, okay? So let's be very aware of the kinds of objects we have. The curl of F, sometimes written like this, sometimes without the parentheses. This is another vector field, and it's defined like this. dq dz I dp dz dr dx j dq dx dp dy. Okay. A lot of stuff to remember here, but we'll come up with a better description of it later. Okay. So what do we notice? It's a vector field, obviously. It has vector components. And this vector field is related to our original vector field, right? It uses these derivatives. So the curl should tell us something about the vector field F. But this is a pretty unwieldy equation to remember. And I imagine that it would be hard, and I forget it all the time. So let's come up with a better way to describe this. And this is a good segue into operator notation. So what is an operator? You can study them you will study them in lots of places. Physics, mathematics, primarily math and physics. But an operator is just a function. It's a function that acts on other functions. So that's the general, there's a technical term, but that's what you can think of. This is just a function that acts on other functions. Operators are functions that act on other functions. And we've seen many operators already. Okay? The derivative is an operator. Right? I just take the derivative.
Does that say operator rotation or notation?
Notation. Okay, so this isn't something new that you've never come across. You just never use the notation, maybe. And there's one particularly interesting operator that we should talk about. And which operator do you think it is?
Gradient, maybe?
Gradient. Right, we've used the gradient a lot. So let's talk about the gradient in terms of operator notation. What does the gradient do? Well, we call the gradient, we give the gradient this symbol. This nabla. And what does it do? Well, so in higher dimensions, it does more. But what does this say? When I do the gradient of f, this is just putting f, my function, in at each of these places, right? Remember, this is a function that takes functions. So the gradient of f is exactly df dxi, df dyj, df dz. Okay. Nothing really sophisticated. It's just a you can think of this as each of these things here is just kind of a placeholder. It tells me what to do, and then I give it what to do it on. Right? Does that make sense? So the gradient operator, this is sometimes called the del operator. Del, or vector differential. These are another ones you're going to look for. Sometimes they're also called the differential operator. So there are lots of terms for the gradient operator, depending on what you're talking about. I don't know any other words for curl or divergence, so we don't have to worry about that. Okay? So I will call it the gradient operator most of the time, or grad. Sometimes I'll write it like grad as opposed to the nabla symbol. So be prepared for that, right? Because it says grad, div, and curl have words, so we can see what's clear. Okay, so what does this say? What are we gonna do? I want to compute the gradient operator, right? This is a vector now, as we already did. New cross product did with F. Okay. So what does this give us? This should give us a vector, right? And what is it? It's perpendicular to F at all times, right? And it points, well, according to the right-hand rule with the gradient, right?
I have a question.
Yep.
You're crossing an operator with a function?
Yeah.
Okay.
Yeah. I'll explain like what that means in just a moment. Right? But you can think of the operator, the output of the operator is a vector, is it not? So I should be able to take their cross product. That's a very reasonable question to ask. So how are we going to set up this cross product? How did we set up cross products? Right, we got a vector I, j, k. The I component, ddx, ddy, ddz, and p, q, r. Right? So now, how do we take the cross product? We compute this determinant, right? So it's I times the determinant of this 2x2 box. So it's d dy times r. So I'm going to give you a, this is a discussion of how we're going to actually do this, right? You said we're going to cross an operator with a vector, which obviously doesn't make a lot of sense on looking at it on the surface, right? But we're doing multiplication here, right? If we were to do this in terms of a normal vectors, right? This would be a scalar, and this would be a scalar, and we multiply them, right? But now this is an operation. I take the derivative with respect to y, and this is a function, right? So if I were to write this, what do you think this should mean?
Is it the derivative of r with respect to y?
Exactly. So multiplication in terms of this operator makes sense, right? Multiplication is just apply the operator to the function.
It seems really convenient. Like,
Yeah, someone thought really hard about all this stuff and came up with appropriate. Well, yeah, that's why operators are convenient. And I'll talk to you about, we'll see a couple other operators that we'll use, but they're very convenient. They make notation easy, but they're also important things that we want to study. So we're going to do this times this minus this times this, dq dz. This is the I component, plus, block that out, dr dx minus dp dz, j, plus dq dx minus dp dy k. Okay, get a little tight on the board there.
Professor, could I pause you at this point to interject a question?
Yes.
It struck me as I looked at this in the book that second sign, I mean the first one actually, you don't see a plus sign before it.
Oh, that's a negative sign here, sorry.
Well, that's what I wondered. In the book, most of the time they have it as a plus sign.
Yeah. So
The one example I found had it as a minus sign, and that seems so wrong to me.
no, okay. So when we're computing the determinant, we alternate signs, positive and negative. So this is a plus sign, this is a negative sign, that's a plus sign. That is always going to happen when I take a determinant, every time. Okay? But if we compare this to the curl that I wrote earlier, which is, oh, right here, we can still see it. Look at that awesome planning. What's the difference between this and this? This middle term, right? This middle term says dp dz minus dr dx. I have dr dx minus dp dz, but I have this negative sign here. So they absorb this negative sign into here and switch the order. Okay? Does that make sense?
Yes, thank you. I'm
So
giving a thumbs up, but I guess it wasn't on camera.
yeah. So what you want to remember is when you compute a determinant, you always switch sign every time, right? Positive, negative, positive. Okay? And in this case, we have an extra negative sign here. So what does this say? This is equal to the curl of f. So this is often how the curl is defined.
What is a curl?
Like, what does it mean, or what is it? Because it is this. It's this. It's a vector.
Sorry,
It does
the
that.
first one then. What does it mean?
Yeah, we'll talk about what it means in a minute. Okay. But let's talk about what it is first. It is just a vector that's related to our original vector field. I can compute it by doing this. Okay? Curl of f is the gradient operator across the vector field. Okay? So if you're ever asked to compute the curl, which you will be, you can either remember this formula, which you'll probably forget because I forget it all the time. I just did this like 10 minutes ago and forgot. Or you can remember this in its operator notation, and they go through this process, which you're very familiar with. Okay? But either way, you're going to have to be careful about computation because there are steps there that can be mistaken. Okay? So let's talk about, well, any questions on what is it and how to compute it before we move on to what it means?
I kind of have a question.
Okay.
That K component part, that's the kind of the same as what we were doing on the other page up at the top left, the dq dx minus dp dy, or one of the, yeah, that area essentially. Are those related at all? Or I mean, obviously.
Yeah, so like I said, we're going to, this is Green's theorem. We're going to formulate Green's theorem in terms of curl and the divergence. So this is right here, the curl of something.
Yeah, that's what I was,
Right.
because you see it on the other side too.
Yes, well, it's actually the K component of the curl.
Curl.
And so we'll see a formulation of Green's theorem in terms of curl and divergence. And the reason that's of interest is when we move on to Stokes' theorem and the divergence theorem, when we start talking about flux, they formulate their integrals in terms of curl and divergence and gradient. So that's why if you looked at that both div grad curl, that's really the three main things you're going to need to know to apply vector calculus. And all the integrals we talk about describe their integrands in terms of div grad and curl. Question?
I have a question.
Yep.
So, the determinants, so if we consider it as a vector, does it have a magnitude in this case?
This right here, this has a magnitude, does it not?
The
This-
new vector.
Oh,
But-
this?
What about the determinant though, on its own? Is it just like
Oh,
a direction or?
so I don't know what you mean by that, but I'm going to guess what you're asking, and then if I'm wrong, tell me. So the determinant is, in a general sense, a number, right?
Okay.
So But in this case, we produce a vector because it takes this vector and
Mhm.
makes some sneaky use of the multiplication operation, right? These are three different kinds of multiplication right here. Right here, this is vector operation multiplication. This is scalar multiplication,
Yeah.
right? So we're abusing the shit out of the multiply term. It means three different things right here. Okay.
Okay.
So the determinant itself is a vector now because we're doing scalar multiplication here. And as a vector, it has a direction and a magnitude. But it only has a direction and a magnitude when I pick a specific point,
Okay.
right?
That kind of
Well,
makes sense.
that's
yeah.
not true actually, but it has a direction and a magnitude when I pick a specific point, right?
Yeah.
And otherwise, its magnitude is just a function of x, y, and z,
Okay.
right?
That makes
So
sense,
its magnitude without picking a specific point is a function. And whenever I pick a specific point, it's a number,
yeah. Okay.
okay? So just like whenever I pick an x, y, and z, I have a vector in my vector field, right?
Yeah.
Whenever I pick a x, y, and z, I have another vector in my curl, and that vector has length and magnitude.
Yeah, that makes sense.
Okay?
Yeah.
Did that answer your question?
Yeah, it did.
Okay. Let's let's look at what the curl looks like. Judging by the name, it should tell you that something is curling, right? It's about curl, it's about rotation. And so I want to start with the very hand-wavy description of what this does. We're gonna draw some pictures, have the computer draw some pictures, and then we'll try to explain them. Okay, so we're gonna go back to the river analogy that I have talked about a lot, right? A vector field is like a river, right? With many eddies or rocks or just shit in the river, okay? And if I had a ball, let's say I have a ball has and I put a red dot at the top of it, wherever the top of this ball is, right? So I have this river that floats down this way. I don't know if you can see me. I did the, I unmuted I can't, okay, now I gotta, okay, I cannot show myself again. How do I do that? Okay, well, can you see my left hand? Yeah.
We can put you on our big screen if we want to.
Okay, yeah. So, well, I just don't know if you can see my hands or not. So imagine this is the river. It's going down this way, right? And I put a ball. Remember, it has a top, which I've marked with red, right here, right? And it starts to move down this way. The ball clearly isn't going to just float like this. It's going to spin a little bit, right? Because the water doesn't perfectly run this way. There could be an eddy here or a rock, right? Something that makes the water at the bottom come under and the water at the top come over. So as the ball floats down the river, and not only is it moving this way, it's also spinning, right? You can see this in videos of, there's videos of people throwing basketballs off dams and they like drop it and it like goes very far away from the dam. It doesn't just like drop straight down. You can see some of those random videos on the internet. The spinning is happening because the vector field of gravity or the other one of air, what's that word? Air resistance is making it spin. So curl describes the spinning. And what does that mean? If I have a tube, a straight, perfect circular tube, nothing else in it, and I pump water right through it, and I magically put my perfect ball right here with the top up, it will just go straight. It doesn't spin anymore. So there, the curl will be 0. Did that picture make any sense in your mind? So you ever see in movies or videos or whatever, when someone gets flushed down a sewer pipe or something, or gets blasted by a wave, they're always spinning, right? Because you expect some curl in that motion. That spinning is represented by the curl. And we're going to look at some pictures here in just a moment. Okay, but I want to start you off with that very common idea. It's just the rotation of the object as it moves through our vector field.
So would it be the same as like torque?
No. Torque, I mean, torque measures force, and often it measures spinning force, but not necessarily always, right? So what we're used to thinking about torque is like, I have a nut here and a wrench, so I'm turning it. It makes me feel like it's turning, right? But I'm exerting force directly down.
Yeah.
I'm exerting force directly in the motion that I am moving, in the direction I'm moving, right? That's how torque works. Curl is not that way, right? Curl it describes the motion perpendicular to my movement, my motion.
So like another degree of perpendicular, like if torque was perpendicular twice, kind of.
Yeah, we don't want to think about torque here because that's not quite the right analogy,
Like that.
right? So if river goes this way, the curl is going to be pointing this way, right? It's going to be telling me how it's spinning this way.
Okay.
Okay.
If I may, I think one other difference is you have to have a persistent field to have curl.
Yes, you
In the case
need
of-
a field to have curl.
If you're talking about force and torque, as you were saying, it's kind of a one-time thing. When you apply the torque, then there's torque. Yeah. Otherwise,
torque is it's a one-time thing in a one-time place. It's one vector. And we have a lot of vectors in this vector field. Okay, let's look at some pictures. So let's pull this over here. So this is my vector field. It looks like this. Let's draw some more things in here. Let's do 3. Okay. So we're all familiar with this, right? Now, let's draw, this is my vector field, x minus xy. This is p. They have different letters for them. X minus y, this is q, and z, this is r. So let's draw the gradient field here. What is the gradient here? Well, we can't draw the gradient here because this isn't that was a dumb statement because that doesn't make any sense. Okay. The gradient operator we can't really draw, but I computed the curl. This is the curl. Let's go through this operation just to be clear we got everything. So F is x minus xy I plus x minus y j plus z k. Right? So the curl of F, this is dr dy minus dq dz, dr dy dq dz. This is 0I plus dr dx minus dp dz, 0, 0, 0j. I gotta turn this around. Plus dq dx minus dp dy. Dq dx is 1 minus the PDY, which is x, minus x. Okay. So make sure I computed that right.
You can have I guess a gradient or a vector field that has zero curl throughout its entirety.
Yeah.
And that means there's no, like if you put a ball, a particle, any sort of thing flowing through that, it
No
won't,
spinning.
no spinning at all.
Yep. It just moves exactly in the direction that you're in.
So the curl is an intrinsic property of the gradient, like vector field that we're looking at.
Yeah. Sure. We can think of it like that. I'm hesitant to use the word intrinsic and extrinsic because that's when we're talking about like we're going to measure something that's inherent to this object without needing other things, right? So it is an adjective. I say that the curl is a descriptor of my vector field, right? I wouldn't say my vector field has intrinsic and extrinsic things because that requires me to have some notion of geometry of my vector field, right? What is inside my vector field? What is on my vector field? What is not on my vector field? Nothing. Everything is on my vector field.
I was thinking in terms of your river analogy. Like obviously there are things outside of your river that aren't affected by it, but
yeah, but like
who would care about this?
It's well, in short, no.
Yeah.
Right, because we're interested in what's happening in the specific vector field. Okay, so I check if this is correct. I think that's fine. So let's draw the curl. Okay, so this is the curl, 0 I plus 0j plus 1 plus xk. Okay, and this is exactly what I was expecting. Okay, so how do we rectify this? If we look at just this part, there's clearly some curling here, right? If we drop the ball right here, it does this. It slowly comes this way, following the vector field, right? I think I can do that. No, it doesn't do that. That's unfortunate. Maybe if I do restrict view to 2D. Oh, come on. That's stupid. It doesn't do that now. I don't know how to make it do that. But we can see, let's get rid of some of this stuff so we can get a better picture of the curl. All the blue stuff, if I drop my ball here, I'm going this way and moving a little bit, spinning a little bit. And if I go this way, I'm moving this way and spinning a little bit. So you can think of the direction of the curl as the right-hand rule, right, which we expect. So do you see my hand here? So you point your fingers. The fingers are going to be the direction of the vector field, and then my thumb is going to be the curl. Right, so I move from the x-axis. First, I'm pointing at the x-axis. I move to the y-axis. That's the curl. So right here, I'm pointing at the x-axis. I'm curling it in the direction of the curl, of the rotation, and my curl should point up. Right, that's what we get here. Here, okay, the curl points down. So why does that happen? Well, I point my thumb in terms of the x-axis, my fingers in terms of the x-axis, curl it in the direction of the vector field, which is this way, right? It's going this way. So my thumb should be going down. And that's what this curl does here.
Is the magnitude of your curl vector the speed at which it like kind of rotates?
Yeah.
Or-
I think it's twice the speed technically, but that's just some random computation that came out. Maybe it's this once the speed. I'll have to check the exact number, but the magnitude of my curl 100% describes the rate at which I'm spinning. What factor I forgot. It could be 1, it could be 2. I think it's 2 for one of those random reasons where 2 shows up. Okay. That would be a quick look up in a book. Any questions about what the curl means?
It's very interesting that since it's 1 plus x, you can see the length, the magnitude of the red arrows growing to the left. And then as you get over to the right and they start going down, I assume that you've got short ones where we can see them, but further out.
Yeah, so as we get further out, these get longer, right? And then it gets negative right about here at 1, right? So at this point right here, when x is 1, there is no curl. Notice how there's no red arrow right here.
Looks like -1.
Yeah, negative 1, that's what I meant, sorry.
Axes are reversed.
Yeah. -1, because we get the equation here, 1 plus x. So when x is -1, this is the 0 vector. Right? So this whole, if we drew a curve right here, or a plane right here at x equals -1, all the vectors on that plane would have curl 0. Right? So that's to say, if I drop the ball at that spot in my river, it would move without spinning. It's just that one magical spot. If it stayed there, it would move without spinning.
It's supposed to be calm in the middle of the maelstrom.
Yeah.
Yeah.
That's exactly what that's describing. Assuming that I can stay in the middle, which not super common. Okay. The curl is not an easy thing to really conceptualize. There's an interesting problem related to the curl in the homework. It's number 37. I think it's worth exploring a little bit. It talks about how the curl describes rotation of rigid actions, of rigid objects. Right, so it gives you another description of curl. Okay. So what's the purpose of this? Why do we care about curl? Well, what's really nice about this is if f is a function with, function of 3 variables, that has continuous second order derivatives, the curl of the gradient, this is now a vector field, is equal to 0. So when we have a nice vector field, let's try to rephrase this in a different way. What kind of field is this gradient of f? Quiz question.
Vector field?
It's a vector field. What kind of vector field is it? We have a special name for vector fields like this.
Does it start with a C?
It does start with a C. Conservative fields. Right? So it says the curl of a conservative field is 0. Everywhere.
Are you saying that like a function that a function of 3 variables that is continuous, that has continuous second derivatives, is a conservative field?
No, this is a conservative field. The gradient of f is a conservative field. What does a conservative field mean? It's a vector field that is the gradient of some function, right? So by definition, gradient of f is conservative. And this says the curl of a conservative field is always 0. The curl
I thought for something to be conservative, it had to meet some like not expectations, but like it had to.
It has to meet some criteria. Those are ways that we can check if it's conservative. But what does it mean to be conservative? I mean, it is the gradient of a function. That's the definition. How do we check the definition? We have other ways to check the definitions. In special cases, when the field has dimension 2 or 3, we'll be able to check them, or to check if they're conservative. Okay. So this says the curl of conservative fields are 0. If I get a vector field with 0 curl, is it also conservative? This is one of our ways to check. What do we think? So let's look at this field. xzi plus xyzj plus minus y squared k. Is this field conservative? Meaning, is there a function in 3 variables that has this as its gradient vector? There's lots and lots of functions. I don't know if I can check them all. Probably can't. I can try to just integrate these, but I might get equations I can't solve. That doesn't mean they're not solvable. That just means I can't solve them. So we can check if this is conservative by checking if the curl is 0. If the curl is non-zero, then this will not be conservative, right? So let's compute the curl. Curl of f. This is r dy, 2y minus q dz, which is 0, plus p dz, x minus r dx, which is 0, j, and I don't even care what happens because this is non-zero. We only need to check that it's not the 0 vector. No. I made a computation error, but that's fine. This is still non-zero. So a vector field that is conservative must have 0 curl everywhere. Does that make sense? Let's draw a picture.
Question, Professor.
Yep.
So is this like an alternative way instead of using the derivative one where we see if they're equal?
Well, the derivative one only worked when my vector fields have dimension 2.
Okay. So in 3 dimensions it doesn't
We
work.
only formulated that in 2 dimensions. We could not do it in 3 dimensions, right? But you can see that in 3 dimensions, this is a generalization of that, right?
Oh.
Because if we want, so that's a good segue into this. So let's say I have a vector field in 2 dimensions, right? So this doesn't exist because there's no R function. We can think of R being 0, right?
Okay.
So this is 0. This is also 0 because there's no Z variable, right? This is 0 because there's no R. This is 0 because there's no Z variable. So all I'm left with is this, right? And this needs to be 0, which is our exact same thing we just had, right? So this is a generalization of that criteria to higher dimensions,
Gotcha.
to 3 dimensions. It doesn't go up higher than this, right? It's a good observation. Let's look at a picture here. This is our favorite function because it's by the default function. Let's draw its vector field. Let's take some derivatives of it. Oh, that's not what I want. Take the derivative. Why can't I copy you? This is in the x direction. This is in the y direction. And the z direction is 0 because there is no 0 here, right? So this is my gradient field, right? Looks like this. And then if we compute the curl, well, we can see it right now. Can we see it? Well, if we computed the curl, we would just, and we try to draw it, we would get nothing. The curl should be 0. Completely. Okay. And why? Let's think about that in a intuitive way, and then we'll talk about it in a technical way here. So let's look at this equation right here. What does this say? This is, let's look at Q. Q is the derivative of f with respect to y, right? If my field is conservative. Let's go over here. So this is a proof, not really a proof, but a discussion of why this is true. So if f is equal to PQR and gradient of f is equal to f, what is P? P is then the derivative of f with respect to x. Q is the derivative of f with respect to y, and R is the derivative of f with respect to z. Right? So let's look at this right here. Remember, it has continuous partial derivatives. So continuous second order partial derivatives. So the curl here, well, I guess we can see over here, I can just point. Let's look at this term right here. It says this is the derivative of q with respect to x, right? So dq dx is df dy, and then you take the derivative with respect to x. Right? So this is the second order, the mixed partial derivatives with respect to x and y. Correct? And this is the mixed partial derivatives with respect to x first, and then with respect to y. And those should be the same, because order doesn't matter when I take the partial derivatives if my derivatives are continuous. Right? Order doesn't matter when you take partial derivatives when the partials are continuous.
Could you do that one more time?
Should I say that one more time?
Could you say that one more time? The
Order doesn't matter when you take partial derivatives if the partial derivatives are continuous. What I'm trying to say is, i.e., df squared dx dy is equal to df squared dy dx, right? We say this all the time when they're continuous. Okay, so this is why this theorem is true. This proof, nothing sophisticated there. Okay, we're spending a lot more time on curl than I anticipated. Okay, so any questions on that? Nope. Okay. So there's another theorem here, which is the converse of this one. It says if f is defined on all of R3 and the component functions have continuous partial derivatives. We don't need all partial derivatives, just continuous single partial derivatives. Then, if curl of f equals 0, this implies that f is conservative. So what does this say? This is the converse of the previous one. We said conservative vector field implies 0 curl, and in this situation, 0 curl also implies conservative vector field.
Wait, what does it say if f is
Defined on all of. Okay. So we can go check if a field is conservative or not quickly by computing its curl. Just like we could check before by computing those partial derivatives. Okay. Any questions? Ugh. Okay. Okay. Any questions? No questions? Nope. So the book has some other descriptions about what curl is supposed to mean. Like I said, exercise 37 is one. There's another description on page 1146. But yeah, I think you need to just spend a fair amount of time working with curl to get used to it. Okay, so we talked about curl. What's the other object of interest we're going to talk about today? The divergence. Okay. And the divergence is I think, easier thing to describe. Okay. So what is the divergence? The divergence of a vector field, div f, this is equal to dp dx plus dq dy plus d r dz. If f is equal to pi plus qj plus rk. Any questions? It's very easy to compute.
Those are full-on derivatives, not partials, are they?
No, they're partials.
Okay, you didn't curve the d's. That's what I wanted.
Yeah. My my d's are not super curvy in general. I always do them like this when they're partial, and I do them like that when they're solid. So, or if I just wrote better, we wouldn't have this problem. But that's been a sore spot in my evaluations for almost a decade. Okay. Very simple idea. So let's do two things. We'll talk about how to compute it and what it is, and then we'll talk about what it means. Okay? So how do we compute it? This. Take some derivatives. How else can we compute it? What does this look like? Let's relate this to the gradient operator somehow. So what does the gradient do? It takes the partial derivatives with respect to each one of these one time, right? So this is essentially the dot product of the gradient and f. Right? So what does that mean? Well, the dot product of gradient and f, this is ddxi plus ddyj plus ddzk dotted with pi plus qj plus rk. Right? And how do I compute this dot product? This thing times this thing. This is dp dxi, I squared, so that's nothing, plus dq dy plus dr dz. So this is equal to the div of f. The divergence of f is the gradient dotted with the vector field, and the curl is the gradient cross-producted with the vector field. Okay? Any questions? Nope. Okay. So what does the curl mean? You can think of, I think the curl, sorry, we just talked about curl. We talked about curl for an hour. The divergence. What does the divergence mean? So looking at this equation, what do you think it means? Let's just try to describe this. So first, it's a scalar, right? It's not a vector, it's a scalar. It's one number. And it describes how my vector field spreads. Because what does this say? This is how p is changing in the x direction, right? That's what this derivative means, derivative of p with respect to x. And p is the x component of my vector field, right? So this part means how the x component of my vector field is changing with respect to x in the direction of x, right? This is how the vector field's y component is changing with respect to y, right? And this is how the vector field's z component is changing with respect to z. So the three of these together tell me how my vector field is changing or spreading away from any given point. Right? Imagine if these numbers were bigger, what does that mean? That means that my vector field is changing greater in the direction of x, in the x component, right? So divergence measures a spread, okay? And this is another description of fluids. So if I have a water balloon, for example, right? And it's full of water, obviously. I guess that's not a super great example, but sure. And I push in one spot, it kind of distributes the water somewhere else, right? And the water balloon is pretty soft and movable. That's a shitty description. Okay, redo. Let's talk about another water example that doesn't suck so much. Let's put water in this really hard steel can. It's a cylinder shape, really solid, right? And imagine this can is like impressively strong. Okay? And water is a fluid. Most liquid, all liquids are fluids. Gases are also fluids. A fluid is an object that changes to match the shape of its container, right? So if I had a cylinder can right here, full of water, and a hydraulic press that pressed down, right? If I had air in there, I could ideally compress the air, right? That's what they do all the time. They compress air. But water is not a compressible fluid. You're not going to compress the water. Most liquids are incompressible or moderately incompressible. Water is extremely incompressible. Okay? And so if you can think of, what does this have to do with divergence? You'll see that if the divergence of my vector field is 0, that means that F is said to be incompressible, which relates to the incompressibility of fluids. Right? It says, right, well, we can say, it says how things spread, right? If they're not spreading, we can't compress them because they're still there. Right?
Question.
Yep.
Actually, so if you were to take the dot product as if it was like a vector A times vector B cos theta, that thing. So it would be kind of like we're projecting one vector field over the other, right?
So this is not going to work in that sense. And that's a good observation to bring up, because this dot product is really only taken in this formal sense, right? Because what do I mean formal sense? We're doing multiplication here, right?
Yeah.
And this multiplication is defined by taking this operator and operating on P, right? So that's how we're defining this multiplication. If I chose to do this, this part makes sense. This has a length at a given point, right?
Yeah.
But what is the length of an operator?
Yeah.
So operators have length, they have magnitude, but we didn't talk about them, and we won't talk about them.
You said if it has a specific point, it could have a.
If this has a specific, so the operator needs a little bit more to have magnitude. It needs to take a specific function first, right?
Okay,
And
yeah.
then it needs to have a specific point on that function.
Sure.
So the operator takes functions, and so it doesn't necessarily take, well, it doesn't take points. So consequently, it won't have a length until we give it a function and a point,
Okay.
right? So that's a very good observation you made there, is that we're not really, this is not the same dot product that we used, because we're using different multiplication, right?
Okay.
This is a different multiplication operation than we're used to. I'm not multiplying two numbers together here. Okay.
Gotcha.
This is
But
operator notation. So
Graphically speaking, though, is it still like they're overlaying, or like is that what the spread is? How the change would be affected if one was in terms of the other?
yeah, we could think of it like that, because what happens here is that we can sort of think of this as a function already, right? Taking P. So we're giving it functions and we're giving it points, whatever points we had here and these functions. So we could think of this as some sense of overlapping between the gradient vector, given the appropriate function and appropriate point, and my vector field, right? But the difficulty is that we can't draw this vector field, right? This isn't a vector field,
Yeah, sure.
right?
Yeah.
This is an operator, so it has no real geometric sense at the moment. We can't plot it like we can plot this one.
I got it. Okay.
By a similar token, does that mean that we can't draw any conclusions when this dot product is 0? If it was
Yeah.
a dot product, okay.
Well, yes and no. We can't draw the same conclusions we're thinking about. And what I mean is, yes, when the divergence is 0, we can draw conclusions, but they're not the same conclusions as we originally drew, like two vectors are orthogonal, right? When the dot product is 0, two vectors are orthogonal. That doesn't mean the same thing here. Okay, that's to say this gradient operator is orthogonal to my vector field at all points, which doesn't really make a lot of sense, because this isn't a geometric object to define orthogonality on. Okay. If you want to talk about it in the very highbrow sense of operators, yes, you could. We obviously won't. But those operations are discussed a lot in physics and math when you talk about inner product spaces and Hilbert spaces and Banach spaces. So when you talk about quantum mechanics, you use a lot of stuff about Hilbert spaces and operators, and linear operators in particular. So they will define things like orthogonal operators and orthogonal functions and things like that. Okay. And they have their place here, but we're not going to talk about that. This is an interesting place in math, is there's lots of really cool shit that's happening, but a lot of it is really complicated. So when you will go see, I mean, many of you will take physics and things like that, or advanced math, you'll see these ideas show up again in a much more general sense. Okay.
I have a question.
Yep.
Is divergence the gradient of a vector valued function?
No.
No.
Divergence is a scalar, right?
Hmm.
So it should not be the gradient of anything, because the gradient of anything is a vector, right? So that's the first thing. The equivalent object of a gradient of a vector value function should be a Jacobian. And we talked about those in section 15, right? So
I
Yeah.
guess the reason why I'm asking is when taking the gradient of a normal function, you take the derivative with respect to x, y, and z of that function, and then that's your gradient.
Yep.
And here it looks like we have our function f, which is defined as p of I, q of j, and r of k, which each of them are their own functions. And we're taking the derivative with respect to x of our x portion, y with our y portion, and z with our z portion. That's why
Yeah.
it looks like we're taking the gradient of.
I mean, it should look like that because we're dotting it with the gradient. That's what
Yeah.
we just did, right? But we're not this gradient is not operating on this vector field. The gradient doesn't operate on a vector field. It operates on a function,
Mhm.
right? It only takes one function. It operates on one function. The gradient itself operates on one function. It doesn't operate on vector valued functions.
Okay.
Uh-huh.
Hmm.
Any questions? No. There's one interesting thing I want to talk about. Well, a couple interesting things I want to talk about. But first, I want to talk about this interesting theorem and how does gradient and curl relate? How do gradient? We already know how gradient and curl relates. How do divergence and curl relate? Right. So if f is p QR is defined on R3, and PQR have continuous partials, then the divergence of the curl is 0. Okay. And what does this mean, or how do we think about this? So if we go back to something like this, let's recall. If I have something like this, A cross B, what is this? This is a vector that's orthogonal to A and orthogonal to B, right? So if I take this dot product with A, what do I get? This vector right here is orthogonal to A and orthogonal to B. Its dot product with A should be
0.
0, right? When two things are orthogonal, their dot product is 0. Seems obvious, right? So now let's rewrite this in terms of our operator notation. The curl, so we're going to take the divergence. The curl is the gradient operator crossed with our vector field, right? And the divergence is the gradient operator dotted with our vector field. So do we see the similarity between this and this? We're taking a cross product and dotting it with something that should be orthogonal to. Of course, like I just said, orthogonal to this operator is not a well-defined notion in our sense at the moment. Okay. So we can go through the definition, and this is a very easy proof. If you are thinking about this, I think it's a good exercise to just do this without looking at the book solution. Proving this statement is pretty straightforward. Okay.
Question.
Yep.
Would it be the same if you dotted it with the gradient of the function?
Gradient of the function. No.
Like of f, yeah.
No, because well, no, it won't. And why won't it? How do I describe that? First, what function? We don't know if f is a conservative vector field or not, right? We have no idea if f is the gradient of something else. If f is the gradient of something else, this is already 0, so we're done. Right?
Yeah.
So we don't really have an f to talk about yet. If we did have an f, this would be clearly 0. The curl of a conservative field is 0.
Gotcha.
Okay. So I want to end this discussion on divergence with another operator of interest. So we said that this is equal to divergence of f. Okay. Now, if f is conservative, i.e. df is equal to f, then divergence of f is equal to, which is equal to this, f, lowercase f. So all we're really doing is taking two derivatives, right? And that says that the divergence of f is df squared dx squared, df squared dy squared, plus df squared dz squared. You can follow this through just the basic definition of divergence. Okay? And why do I bring that up? Sometimes this is written as this operator. Sometimes this is written as nabla squared. This is the gradient operator times dotted with itself. So if f is conservative, then divergence of f is sometimes written as nabla of f. And this is another operator of interest. We won't talk about it too much. Well, I don't think we're going to talk about it at all, but I could be wrong. Other than today. But I only planned up today, so maybe we'll talk about it when we talk about Stokes' theorem. This is called the Laplace operator, or Laplace's operator. It is called Laplace's operator, or Laplace, Laplacian, the Laplacian. So these are two terms for the same operator. And this operator is particularly important when we talk about harmonic functions. So heat, waves, airflow, very, very important operator for things that are harmonic, that can be described by waves. So when you are taking physics and you talk about the wave equation, that's Laplace's operator. Okay, so you will talk about the wave equation when you talk about the wave equation. Probably E and M. Seems reasonable. No. Classical mechanics for sure. You take a course of classical mechanics, and if you want to go do engineering of some sort, you probably have to know classical mechanics because that's how buildings don't crash and shit. So you will see the Laplace operator when you solve the wave equation. You'll solve the wave equation when you take classical mechanics. It also shows up when you talk about heat and things like that. So pretty important operator, though we won't talk about it now. Add more than this. Sometimes it's written like this. This is the more common way that I've seen it written, is this capital, this normal delta symbol. So one of these is the gradient, and then turn it around is the Laplacian. But the book talks about the Laplacian like this. It uses this symbol. And sometimes I use this symbol too. I've seen it mostly like that, but who knows? Things have changed probably. Okay, so we can write the divergence in terms of the Laplacian operator if the field is conservative. That's what this whole discussion is about. Okay, any questions? If you want to get anything out of this discussion, what we're talking about here is operators are useful. They will show up in a lot of places when you start doing more math, especially if you do more math. If you do physics, they'll also show up. You'll get linear operators when you talk about quantum mechanics. You'll get Schrodinger operator. We also talk about quantum mechanics. You'll do the wave equation, which is Laplace's operator. The heat equation, which is also the Laplacian. What else is there? There's probably others that I didn't plan for. So this notation is not going anywhere if you continue to study math or physics. So remember it here. So lastly, we're going to talk about Green's theorem in relation to these things. So like I said, we're going to reframe Green's theorem in terms of divergence and curl. And we're going to move forward with that when we talk about all of our other theorems. Green's theorem revisited. Okay. So let's look at Green's theorem. I just said the integral over C, I'll put a closed curve there, dot dr. This is equal to the integral of p dx q dy, which is equal to, by Green's theorem, double integral over dq dx dp dy dA. Okay. So what does this look like? This looks a lot like one of the components in our curl vector, right? Nick is pointing at things. So
That's
which
what I
one?
said. That's, earlier when I was.
Yeah,
yeah,
it does. It is, right? And which component is it? So
the K1.
the K1. So we can rewrite this as the integral over D of the curl of F dotted with the K vector. Okay. Does that make sense? So I want to express this in, if I were to compute this, I would not go compute the curl and then do this. That sounds like a lot of effort. I would just do that because this is 2 dimensions, right? But the reason we're expressing it like this is because we're going to want to generalize this idea, and it will generalize using the curl and the divergence. Okay? So we're going to talk about 2 more theorems here, Stokes' theorem and the divergence theorem. And I've said they're all examples of Stokes' theorem. And that's technically not true, but also technically true. So the Stokes theorem that we will cover is a special version of Stokes theorem. And the Stokes theorem I often think about is the generalized version of Stokes theorem. So the generalized version of Stokes theorem describes Green's theorem, Stokes theorem that we'll see in chapter 16.8, and the divergence theorem, which we'll see in 16.9. And when we get to it, I'll point out the general version of Stokes theorem for a little bit. And the reason we need to talk about divergence and curl is because the general versions are stated in terms of objects like that. And they link Green's theorem, Stokes theorem, and the divergence theorem all together. Okay? Any questions? Interesting side note, if you are interested in Maxwell's equations, you literally have every tool you need to go prove Maxwell's equations. It's just simple vector calculus. I don't remember Maxwell's equations, but every tool that you need to solve to prove Maxwell's equations, you can do right now.
Professor, it's interesting because there was no vector analysis at the time he was doing his work. They were using a primitive version called quaternions.
Yeah. Yeah. They are, I wouldn't say they're, quaternions are not quite primitive because they're still quite useful, but not a unified theory like we have vector calculus now. So quaternions do show up in a lot of other areas of physics. So it makes sense that he was using them. They'll show up in quantum mechanics a lot. The answer seems everything shows up in quantum mechanics. So it was useful at the time. That's a pretty common thing in math. You have some theorem that is right, and you can prove it in these special cases, and then later someone comes along and makes it very nice and general and cleans it all up, right? The first person who thought about the gradient didn't have a nice operator notation for it that made everything work out. They said, I'm just going to take some derivatives and I'll make a vector out of it. That's probably exactly what they said. Okay. Any questions?
There's something on the original schedule about a test on Thursday, but that's no longer the case, is it?
No, there's a new schedule, which I posted. It should have, if you look at the syllabus, it should have, the date is version 2_3. Why is it version 2 twice? Okay, it's version 2 with the date March 25th. It does not have a test on Thursday. I hope not, because I didn't write one, and I don't really want to write one.
Says there's a quiz.
Yes, okay, there's a quiz, as there should be. Yeah, just a quiz. There are no more tests until the final, because we were all in this, like, because we lost a week.
Yep.
Yes, so please don't look at the old version. You got to look at the new version now. It's also up in Canvas. While we're here talking about that, so we can go through this a little bit. So we just finished this. We're gonna have a quick quiz. And remember when I told you to learn about parameterization and you're gonna do it a bunch of times and it's never gonna go anywhere? We're doing it again. So we're gonna parameterize surfaces. And I'm gonna bet no one listened to me then, but we're doing it. So I would go and retroactively listen to me if you are struggling with parameterization. Because we're gonna parameterize surfaces, not just curves now. And why do we care about surfaces? Because we want to use Stokes theorem and divergence theorem. And what are these things? They measure flux, right? Imagine I have a net or a cell membrane, something that's very permeable. And I have a fluid that flows through it, right? Some of it's going to get caught. Some of it's not. How much goes through? That's what flux is. And is, as you can imagine, that's a pretty useful measurement to have. Right? You can think of things that absorb sunlight. right? How much of it stays here and how much of it gets reflected. So things like that is the topic of our next study. So these two sections will be more like theoretical sections. We just need to know how to do this. We need to know how to parameterize. We need to have these basic tools to do the stuff in these sections. Okay? So we're nearing the end of our tunnel. We've only got 2 more classes and a final, 3 more classes and then a final. The final will be cumulative. So yeah, wow, that's really fast. It's only 2 weeks and then the final. So on this day, the 30th, come with lots and lots of interesting questions that you actually tried to do first. Tell me where you got stuck on them, and then we will work on them. If you have any questions during this time, you can send me emails or set up office hours. I mean, to do office hours, I just have to move from my work desk to this desk. So it's not like impossible for me to do. I don't have to drive to campus or anything. So we can have more office hours near the final if we need them. But if we need them, requires that you actually ask me for them. Okay. We'll end a bit earlier today. Any other questions? This is really cool math. I'm really excited about all this cool stuff we get to talk about. And it has, people think, so I think it's cool for 2 reasons. One, the less cool reason is it has applications and stuff. People care about those things. I myself never really did. But they are there, so I can talk to you about shit that has applications. Some people quite care about that. But on the other side, it's just really elegant, clean math. You have really complicated topics and complicated ideas that are really succinctly described by simple equations, which I find quite nice. So we'll see the end of that next week when we talk about Stokes' theorem and the divergence theorem. And then remember, both Stokes' theorem and the divergence theorem and Green's theorem are all special cases of the generalized Stokes' theorem and the fundamental theorem of calculus. They're all special cases of generalized Stokes' theorem. Okay. Have a nice day. Oh, did you have any last comments?
Professor, I have a question.
Yep.
Where do we go to like rewatch the recordings of the lectures?
Oh, okay. If you, so the recordings are up, most of them. I'm gonna put my last app's pictures in there. If you go to Canvas, let me go to courses. I think if you go to pages, so it should look like this. If you click on pages,
yeah,
it'll have the lectures. This is
oh
from
yeah, I see it.
16, and you click on it and it's embedded. Yeah. Click on that.
Okay, I see it now.
Yeah, you can also view these on YouTube since I couldn't load them into Canvas because it take too much space.
Okay.
This is my first YouTube video. Well, these are my first YouTube videos.
Thanks.
Okay. Any other questions? Question, Nick?
I'll just say you can make a channel of you doing math for fun.
That'd be a pretty shitty channel. Okay. So we'll see you on Thursday, because today's Tuesday. Have a nice day. How do I close this?